Analysis and qualitative effects of large breasts on aerodynamic performance and wake of a Miss Kobayashi's Dragon Maid character by N. Rabino. Article info. Keywords computational fluid dynamics, ANSYS, drag coefficient, human aerodynamics, SSTK model, anime, Quetzalcoatl, titties, and thick, AMS subject classifications, 00A72, 76-5, 76G25. Abstract. A computational fluid dynamics methodology is used to study the salient flow around the breasts of a human figure and to describe the aerodynamic differences imparted by their geometric presence. Two models are proposed for examination. A three-dimensional reference based on a character design with a significantly buxom figure, and a modification of this design where the breast size is reduced significantly. The two models are tested at speeds ranging from 1 to 30 miles per second squared, using Reynolds averaged Navier-Stokes (RANS) drag, lift, and skin friction forces along with turbulent kinetic energy (TKE) are investigated and compared between the different models. The present results are expected to provide useful information on the validity of the statement "flat is justice" in terms of an aerodynamic standpoint. In addition to this, the results can offer worthwhile data investigating the anthropometrical presence of large breasts on sport aerodynamics. Section 1. Introduction. The aerodynamics of the human form has been an area of valuable research in various aspects of sports and competition. Air resistance, hereinafter referred to as drag, is a concerning factor in many time-based trials, and enhancing potential efficiency can be done through the elucidation of the flow around the human figure. Studies concerning the drag of the human body using wind tunnels can be found dating back to the 1920s. A small sampling of subsequent studies exploring the effect of drag-covered areas as running, cycling, skiing, and skating, all of which reinforces the relevance of aerodynamic investigation on the human shape in regards to performance. In many of such studies, the authors seek to investigate the effects of positioning in relation to drag, and some utilize numerous subjects of differing anthropometric proportions to describe a generalized result on such positioning. Hitherto, none within the author's investigations has described the effect of physiological features on aerodynamic performances in great detail. Stemming from certain internet communities and pertinent to the era comes the succinct statement "flat is justice," which consequentially begets interesting debate that can reverberate and diffuse throughout media. Essentially, the statement describes the appreciation of flat-chested women, which hoists a particular aspect that is yet to be fully explored in human aerodynamics, namely the effect of breasts in regard to drag and overall aerodynamic performance. This work is intended to contribute to the understanding of how large breasts can affect the dynamics of the human wake through the use of computational fluid dynamics (CFD) simulation tools. This preliminary work focuses solely on comparing the relevant effects of large breasts of a selected human design to that of the same design but with euphemistically lesser tracts of land. The following sections will present an overall understanding on the human wake in relation to simplified geometry along with engineering applications, introduce the chosen human geometry and models, relevant boundary conditions, the governing equations, and the numerical methods used to solve the equations. An in-depth view on the computational uncertainty is described, following, and with extensive results and discussion, conclusions, and recommendations for future work. Let me drink my water real quick for this. Section 1.1.
No, you are
Background on the human wake. The human body can be described as a bluff body in respect to the flow around it. Literature around the behavior of the wakes behind bluff bodies indicate that the flow will be unsteady due to the turbulent transition and separation of the boundary layer. A simplification analogous to the human shape can be represented by a grouping of uniform circular cylinders. and therefore existing studies on this type of geometry can provide general insight to the wake region. Sumner et al. Described the wake and development of vortex structures of cylinders with aspect ratios, i.e. height to diameter, of 3, 5, and 9, and determined that a transition in vortex shedding occurs at h to d equals 3. An investigation by Okamoto and Shonabashiri also supports this finding, adding the cylinders with an aspect ratio of 3 experience a recirculation region that extends 4 diameters downstream. Assuming the human form takes a roughly large cylindrical shape near this aspect ratio, it is to be expected that the recirculation region will behave similarly and extend approximately 4 body widths downstream. A readily apparent deviation in geometry compared to studies done on singular cylinders is the presence of the gap between the legs. An extensive and comprehensive view by Zoe and Allam on the various arrangements of 2 cylinders indicate the wake structure falls into a multitude of regimes. In a side-by-side configuration being similar to the 2 legs of a human, it is deduced that there are 3 primary regimes where the wake experiences proximity interference. When closely spaced together, the first regime shows that the cylinders act similarly to that of a single bluff body with a width corresponding to the 2 cylinders. When the gap width is larger than 20% of the diameter, each cylinder has individual wakes that strongly affect one another and is associated with the second regime. At gap widths exceeding approximately 100 to 120% of the diameter, each cylinder acts as an independent body, with the vortex streets being loosely affected by one another. Seeing that human legs are not strictly cylinders with a fixed diameter, but more akin to inverted tapered cylinders, the wakes behind the legs will likely behave in a similar fashion observed in both the first and second regime, with the ankles and calves being narrower and having a larger gap between them. The second regime is applicable. A transition into the first regime can be expected associated with the bulkiness of the thighs and reduction in gap width. Why did I say within? Anyway. Engineering literature can also provide additional details on the flow characteristics around the body. Many of such studies are motivated by exposure control and contaminant transport, thermal issues, and comfort prediction, rather than overall drag effects. Inherently, many of the tested flow characteristics are evaluated in a quiescent environment or at air velocities that are of a lower order compared to those found in sport-related studies. Nonetheless, these studies provide useful insight on the natural turbulence caused by the human form and the unexpected anatomical location of flow separation. Intavong et al. Utilized a high-speed camera to record the wake generation of a 1/5 scaled realistic human mannequin that was accelerated to a velocity of 1 meters a second squared. From the results, it was found that the shoulders undergoes flow separation and produces vortices in a regular pattern. The hands produce a well-defined body, yet unstable vortex sheet that curls towards the center line of the body. The head acts similarly to a classical sphere/cylinder cases, with the addition of a trailing wake formed from behind the neck. The neck was found to remove the expected free shear layer that is present in cylinder studies and thus eliminates the formation of an oscillating vortex sheath. In all, it can be said that the observed human wake is a highly complex and richly diverse system that is easily influenced by the inherent geometry used. It is expected that from this study an overall summary can be presented on how and to what degree the previously described flow structures are affected by the presence of large breasts. Figure 1. Comparison of designs for LUCOA. A. Original reference design, courtesy Kyoto Animation. B. The modified design proposed for comparison. End of part 1.